we talked about protocols. We talked about primitives for a while. We talked about all of the different building blocks. We talked about symmetric ones, asymmetric ones, hashes, ciphers, digital signatures, and key exchange. We talked about how now that we have all of these, we essentially have all the tools to build things on top of it. It is sort of, I don't want to undersell it, but probably 30% of the job of cryptography engineering to actually know how to use these components. The rest is to know how to build protocols, how to put them together, and then another solid 40% is knowing how to put things into the real world. We can talk about that tomorrow. Like, I want to have a whole lesson for all of the realities of doing this. But before we get from building blocks to realities in the middle, there's protocols. And protocols is a term that some people would use more stringently than I do. Everybody would agree that, for example, TLS is a protocol. And TLS is the protocol that secures connections. It's the S in HTTPS. When you go to a HTTPS website, TLS is being used to negotiate the encrypted connection between you and the server. Nobody would disagree that that's a protocol. But I call protocols a lot more things. I call protocols all of the agreed upon and interoperable compositions of primitives in a fixed way. And agreed upon, to be clear, not necessarily between different parties, even maybe just between different computers in your same network, even maybe just between a computer and itself later in time. They're still talking a protocol if they're concretizing some cryptography into the wire. And when I say the wire, it's a bit of a term of art to say the bytes that actually get represented and transmitted. It might be on disk, it might be the actual wire as in Ethernet, it might be radio. But in general, when you hear putting things on the wire, or the wire format, or the wire representation, we're talking about how do they actually look like in practice? How do you actually put them one after the other? Because we've talked about a number of things. We talked about keys and how the keys look like and so on. But we talked about hashes, but we didn't talk about how we send these ciphertexts to the other side in a way that the other side can actually decode and reliably put together. So it's probably fitting to start from TLS, and TLS is also covered in the book, and it is probably almost certainly, it is certain, the most widely used cryptographic protocol in existence, because HTTPS and essentially the entire economy rests on us being able to do things securely in our browsers, and doing things securely in our browsers rests entirely on TLS. The whole browser security model is based on the concept of origins, so essentially the idea that Filippo.io cannot access your chasebank.com data and vice versa. A browser will keep those realms separate, and those realms are called origins in browser speak. But the thing that makes an origin and authenticates who has control over the origin is TLS. If you break TLS, the entire structure on top of it breaks down, because then if you are at Starbucks and you just connect to the Wi-Fi and somebody just intercepts your connections, they could just pretend to be Chase without TLS in the middle to encrypt your data and authenticate that you're actually talking to Chase, so that they can give you things that are to run from the chasebank.com origin. Actually, Wi-Fi is also a protocol. Wi-Fi is also a protocol, and it used to be that open Wi-Fi was pretty much a free-for-all. And these days with WPA3, it's kind of better, although it's weird, and the Wi-Fi protocols are not public. like this is the specification of TLS. It's a public document. It's a RFC. If you want to know how Wi-Fi works, because for example, you're an academic and you want to, I don't know, do a lean model of it, and you want to prove it's secure or not, or like try to figure out an attack, you have to pay a lot of money. And that is a great way to make sure that people don't look at your protocols and that your protocols have really stupid shit in them. So yeah, anyway, Wi-Fi is also a protocol. Let's leave Wi-Fi aside for a minute. Back to TLS. So what is TLS? TLS is a transport layer, so it concerns itself with securing a connection, which is a bidirectional stream of bytes, where messages are not delimited. There is just a long sequence of bytes in the connection that are being sent from one side to the other, and another stream that is being sent from the other side to the first one. There are two parties. TLS is not concerned with multi-party, more than two parties. This is not true of all protocols. There are protocols like the Signal one, the one for encrypted messaging, which instead are concerned with what if we have more than two people trying to communicate securely. Completely different protocol. TLS is concerned with confidentiality. So a TLS connection needs to be encrypted so that if the transport over which you are having the TLS connection is compromised, the attacker cannot recover the content of the TLS connection. And it's concerned with authentication. The server is always authenticated in TLS. So when the client connects to the server always proves its identity in some way. The client can optionally also prove its identity. Most TLS connections are only server authenticated. Mutual TLS authentication is used when, for example, two servers talk to each other and they want to prove to each other who they are so that they will be trusted on both sides. But usually, authentication in the browser is done inside TLS, so it's not TLS is not concerned with it. In the simplest form, with passwords, what you do is that you open a connection to your bank authenticates the TLS connection. So TLS has the job of authenticating that the bank is the bank, but the bank doesn't know anything about you. You are just a browser. And then the browser uses a different protocol, which is not a cryptographic protocol, which is HTTP, to send a request that includes your password, usually if you're logging in. And once you proved who you are with a password, they usually give you back a cookie, and then all the requests you make with a cookie, they're like, okay, this is from you because you previously proved who you are. All of that part inside TLS, not the protocol we're concerned with. There are cryptographic authentication mechanisms, things like passkeys, which you might still start seeing mentioned on websites. Those are a cryptographic protocol, but they also run inside TLS, and it's orthogonal composition. Okay, so those are the jobs of TLS. Does it make sense? Like, is it clear what TLS is trying to do? Okay, we have a connection. We want to encrypt it and authenticate it. It's a connection between two parties. The server is authenticating itself. The client might be authenticating itself. Give me your first idea of how you would build such a thing. Like, what pieces would you use from the past weeks? Go. Like, what do you need to do? If somebody tells you, okay, you've learned a bunch of stuff about hashes and ciphers, blah, blah, blah. Secure me a connection. What do you do?
First, we generate some public and private keys so we can start saying who we are, and then use those to secure a key, a shared key, and then we encrypt everything.
Okay, so step one, we need to know, at least for the server, because the server is authenticating itself. The client is anonymous, so it doesn't really need to have a long-term key, but the server needs to have a private and a public key, and the client needs to know the public key somehow. How is the PKI, which is the thing we talked about, where there's somebody else who's the client whose public key the client already has, who signs the public key of the server. And that is another protocol, which is X509, and how those keys are distributed is another protocol, which is ACME. But let's just magically assume that the client knows the public key of the server, and the server has the private key. Okay, and that is a thing we are going to need definitely for authentication. Then we're going to need to do one thing basically as soon as we start.
We encrypt a shared key so we can.
We need to do a key exchange. We need to do a CAN, or if you have an, if we're pre-quantum, because we need to establish a shared secret such that somebody that is eavesdropping on the connection does not know the shared secret, and that is the job of MLCAN, the thing we looked at. So we're gonna then need to sign something with the public key so that we know that the key that we just negotiated is the one of the server. So we need to bind the shared ephemeral shared secret that we just generated for this connection to the long-term public key of the server. So we're gonna need the server to make a signature over something that is strongly bound. And then what do we do with this shared secret?
I didn't understand the question. I mean, you do the key exchange, and after the key exchange, when you bound the key.
So we said that we want confidentiality and authentication. We want to know that we're actually talking to chasebank.com and not talking to Filippo is totally your bank.com. Right? So if you just do a key exchange, MLCAN doesn't give you any of those guarantees.
Just for the authentication.
You need to do an authentication. And authentication, either you use MLCAN with a public key that is known and fixed, which could be how TLS worked. And there is a draft to make it work like this. And I was having some fun implementing it a couple weekends ago because it's nice and fun. But it is not, in fact, how TLS works. TLS does the other thing, which is using digital signatures to sign something, which we'll see what exactly, but in the simplest terms, a hash of the shared key. So first we establish a shared key, which might be established with anybody, might be with, honest Filippo's bank. And then we ask the server, okay, prove that you're Chase. I know the public key of Chase, hand wave how I know the public key of Chase. So make a signature over the key we just negotiated between us using Chase private key. I will use Chase public key, which I know, to check that signature. And after I check that signature, then I can be sure, okay, I actually negotiated a key with Chase, not with Filippo over there. Does that make sense? Great. Now we have a short key. What do we do? We need to agree on something though. TLS is a connection. Does do the symmetric encryption things we've looked at allow you to encrypt just arbitrary endless streams of bytes and authenticate them progressively? We need to chunk them. We need an agreed upon mechanism to say, you want to send like 10 gigabytes of file, you need to break it up into pieces and send me one piece at a time. Why? Because a connection might be infinitely long. It might be one file, it might be a live stream. TLS doesn't know what's going on inside it. TLS is just an opaque pipe. So when you're sending stuff, you need to break it up into pieces, which involves some degree of buffering, which is actually a pretty hard general network, not cryptographic task. And then it needs to encrypt things in pieces and send them over encrypted in pieces so that the other side can receive the pieces, decrypt them, and put them out in the pipe to the other side. Make sense? And why is buffering a little tricky? So this is a layering issue. You have a TLS stack that's sitting over here, which is receiving a write from the application. And it doesn't necessarily know what protocol, what things the application is doing on top of it. Usually when we say application, we mean the final thing, like Netflix, or like a thing that is the thing that actually does the user-facing things. And instead, we talk about TLS as the thing that sits below it, because we deal in abstractions, right? What TLS presents is, oh, you're used to just having a connection. I can give you that, and the connection will be encrypted and authenticated. And you don't have to worry about encryption and authentication. Just send your video or receive your video and show it to the user. TLS takes care of confidentiality and authentication. And it's very bad when these things leak the abstraction. When you need the collaboration of the application to successfully do your confidentiality or authentication, that's bad because more generally it goes wrong. Generally, the two sides don't talk to each other, right? Imagine for a way that the abstraction can break. Imagine if you did authentication after a while. Instead of requesting a signature from the server immediately, like before sending anything or receiving anything, imagine you did that like after a couple of minutes. What happens to all the data that was sent before? It could have been sent to anybody, right? Because it was not yet authenticated. And the application would have to know, wait, I'm not going to send anything sensitive until authentication happens, because it might not be the bank. So I need to only send things that are safe until authentication happens. This never works. This absolutely never works. When you introduce stuff like this, where there's abstraction breaks like that, systematically there's vulnerabilities and things come crashing. So yeah, TLS is the abstraction that just turns a pipe into an encrypted and authenticated pipe. And to do that, it has to chunk up these just streaming a set of bytes into pieces. And the buffering is a problem because to decide the chunk, say the maximum chunk size is 16 kilobytes in TLS. So if you get a write from the application of 16 kilobytes, it's easy, right? You take them all, you encrypt them all. That's one record. It's called the record layer, the part that does the symmetric encryption, and you send it over. Great. What do you do if you get 10 kilobytes? Do you wait for 6 more so that you can do one encryption and send a single one? Or do you send them off as a single one? As a short one. There is no obvious answer to this. 10 kilobytes, you probably just encrypted and sent it. But what if you have 1 byte? It'd be very wasteful to encrypt a single byte and send it over. Because maybe the application is just giving you 1 byte at a time, but it will give you like 1,000 in a microsecond. It would be much better to take them all, encrypt them all as a single encrypted message with a single authentication tag at the end, and send it over. If you encrypt them one by one, do you remember how long the authentication tag is? The thing that you need to add to make the authenticated encryption? 16 bytes. So if you encrypt these byte by byte, each has a different AAD, you are ballooning up the size by 17x. Because each byte is becoming 17 bytes as you send them over. So there's overhead. And there's the CPU of doing the encryption and so on. So trade-offs, hard trade-offs. There is no obvious answer. The protocol just lets you send shorter or longer chunks. It only has a maximum size. Okay, so does it make sense? The general shape of what we're gonna do, we're gonna exchange keys exchange a shared secret, derive keys using hashes. It's always hashes. Make a signature to make sure that we're talking to the right party, and then use encryption with records to encrypt things going over the pipe. Cool. So TLS went through a lot of iterations because it started as SSL v1, which I don't think ever saw the light of day. Then SSL v2 came about in Netscape, I think, way before you were born. Then SSL v3 came shortly after, and SSL v2 was completely broken. SSL v3 was widely believed to be fine for a while. We've realized SSL v3 was completely broken in 2010. I think it was the Poodle attack. I think a lot of the attacks against TLS have like cutesy names, which I enjoy because it helps remembering them. Nobody remembers what CVE 2016-0134 is, but Poodle, yes. Yeah, see, it's CVE 2014-3566. That's the numbering of the vulnerability. Nobody remembers that, but Poodle. Poodle affects SSL v3. All implementation of SSL v3 are affected because this was a mistake in the actual SSL protocol. There was a mistake in how the protocol was designed. So even if you are using a secure cipher, a secure key exchange, a secure hash, you still didn't have a secure connection because you had this mistake in how things were patterned, I want to say. I don't remember Poodle anymore. We removed support for SSL v3 from Go approximately when I started working on this, so that would have been 2018, I think. After SSL v3, TLS version 1 was made. Why was it renamed? Silly politics, whatever. People still recognize SSL more often than TLS. It is a red flag if you're supposedly talking with somebody technical and they say SSL. They probably are not actually, they don't actually know what they're talking about. If you're talking with someone who is not instead a cryptographer, SSL and TLS can be used interchangeably because they entered the collective mind space that way. And I think it's annoying, nitpicky to be like, actually, what you're referring to as SSL is actually called TLS. If somebody claims to know stuff about cryptography and protocols and calls SSL, now you've got a problem. Right, so SSL v2, SSL v3, TLS 1.0, TLS 1.1, which was a minimal change from TLS 1.0, doesn't really matter. TLS 1.2, which was a significant change and is still in use today, TLS 1.2. TLS 1.0 and 1.1, there's a little bit of usage remaining, but we're trying our best to kill it because it doesn't support a lot of good things. And then TLS 1.3 is the most recent one and essentially what everything uses these days. And it was a big step change in how protocols were designed. SSL v2, v3 were basically just YOLO'd by whoever was designing it. TLS 1.0 and 1.2 were collectively designed, but not really with a robust analysis loop. TLS 1.3 instead had formal methods analysis during the protocol development so that the protocol could be changed to make it easier to analyze and get better assurances about it. TLS 1.3 is a great protocol. Looking forward to the day we can turn off all of the other ones. So this is the specification. I used to have it taped over my wall when I was implementing it. And there's, in particular, a pretty nice diagram here. This is the handshake. So can you imagine what a handshake is?
Two parties just saying hello, it's me.
Exactly. It's the initial exchange of information. Essentially, it's the protocol work that happens before the stuff that the protocol is actually for can happen. It's the initial setup. Generally, we talk about handshakes in terms of flights. So one flight as one side sends stuff to the other side and then waits for the other side to respond. The other side sends back another flight, and we call them flights because they have multiple messages maybe like at the same time being sent, but a flight is a set of things that are being sent without waiting for response from the other side. So flight, client to server flight, pause, server receives, prepares its own response, flight over, and so on. And then we talk about round trips. A round trip is one flight in one direction, one flight in the other direction. Why are round trips important? Because the speed of light is annoyingly slow. If you are trying to do a flight, wait for the flight back from the other side of the world, it's going to take some time. It's going to take like 100 milliseconds, or at least dozens of milliseconds, which add up. If you have a thing that to start needs to do 4 round trips, users will notice. Users on maybe a slightly slower connection that are trying to connect maybe with a server on the other side of the world, that will add up to a second. A second, you lose customers. So protocols generally focus on minimizing the round trips of the handshake. They want to start being able to send stuff as soon as possible. There is a minimum number of round trips though, because we need to establish keys. So TLS 1.3, we talk about it as being either 1 or 0.5 round trips, really. Why 0.5? Because the server can start sending data immediately, together with its first flight. It doesn't have to wait for the full round trip, unless it wants to know who the client is, unless it wants the client to authenticate itself. In which case, it's a full 1 round trip protocol. So, client, server, the diagram makes sense. Like which side is which, and they're talking and exchanging stuff, and these are the flights. Okay. Client hello. Client hello is the first message. It's the yep.
Is this specific for TLS 1.3 or
Yes.
is it general?
So this is specifically TLS 1.3. The concept of round trip, handshake, flight, those are general for synchronous protocols. I also call a protocol, and we're going to talk about other protocols. What time is it? We're going to talk about other protocols after the break, but some protocols involve writing stuff to a file. So there isn't the concept of flights. Those are non-interactive. So, but for interactive protocols like TLS, yeah, we generally talk about flights and round trips. Client hello. Client hello is the first message. And I'm not going to go into the very specific details, but I want you to get an intuition for what kind of things does a protocol need to communicate. And the client hello has a few things. It has the parameters. TLS is a way to negotiate things. And the best way to negotiate things in a protocol, if you have a small enough ecosystem of implementations, is to say there's just versions. There's protocol version 1, version 2, version 3, and version 4. And if you want to change, I don't know, the key exchange from Diffie-Hellman to MLChem, you make a new version which uses that. So you don't have the combinatorial explosion of different things that have to combine. And you can analyze each combination as a monolithic thing. That is what Adam Langley refers to as having one joint, so one place where things, and keeping it well oiled, so exercising that joint enough so that you can update it. TLS unfortunately doesn't do that. TLS offers a bit more choice than that, which has led to significant vulnerabilities in the past. These days, TLS is so well analyzed and the abstractions are done well enough that it's probably fine. But in general, for protocol design, you should try to minimize the different kind of things on which you need to agree with the other side. Ideally, there's which cipher do we use? AES-256. Which key exchange do we use? MLK. Which signature do we use? MLDSA-44. Remember the things about parameterization being like a named set of parameters. I showed you the table of MLDSA-44, 6587. And I said that is very useful. Why? Because then when we're trying to agree with the other side, at least there's a thing with a name. And we can either say this protocol uses that one, and that's it. Or if we have to, like in TLS, we can send over which ones we support, but by name. So we don't get to select weird parameters that have certain weaknesses intentionally to try to do something weird. We can only say MLDSA-44, MLDSA-65, and so on. So that's what you're seeing there. The signature algorithms, the key share, the key share we'll talk about in a minute. But in general, those are lists of things that are supported by the client. And those lists use a thing called a registry, because again, ideally TLS would just support one. But if not, we need to have a way to agree on which is which. Like, how do I say I support this, this, and this? I need names. And that's the job of IANA. IANA is the International Internet Assigned Numbers Authority. And you go to IANA and it has all of these registries. And for example, if you are wondering, hey, which signature are we going to use? So what signature are you going to use on the certificate? Sorry, ignore the certificate part. Which signature are you going to use to prove who you are? We go over here. Here is the list of the ones that exist. And the client will send a list of these numbers. Ignore the reserve for backwards compatibility. There are stories behind some of these registries. Like this stuff evolved over 20, 30 years. But here, if the client knows how to verify MLDSA-44 and MLDSA-65 and MLDSA-87 signatures, it's going to send 94, 95, 96 as the list. And that's it. That's how it tells the server, you've got to use one of these signatures. And there's the same for hashes, there's the same for ciphers, there's the same for key exchanges, which are called groups for no good reason. Well, for legacy reasons. Where are they?
Each one of these links is one parameter that we need to send with the first block.
Yeah. Or, one that at some point was being sent. Some of these are legacy and they're not used in TLS 1.3 anymore. But yes.
How would I say, okay, now I'm specifying the names of my hash algorithms and
Those are encodings. And how they're encoded is that the client hello has a certain structure. I can show you. This is the structure of the client hello. It starts with those bytes, then it has some random bytes, then it has some stuff that is not used anymore, and then here's where you put the ones for the ciphers. And then this is also legacy because the client hello is annoying because you don't know the protocol version of the other side when you send it. So it might have to be readable both by a TLS 1.2 server and by a TLS 1.3 server. So there's this game of keeping backwards compatibility all the way back to TLS 1.2. Anyway, and then there's these extensions. Extensions are things like the signature algorithms. And an extension has itself a, guess what? Number. These are the various signature schemes, the same ones that I showed you in the other page. This is just that page So this is one specification. This specification can never change. After it's been published, it's set in stone. If you want to add one to this, you publish a new specification that adds things to that page, which is the page which instead has the list of all of them. And the signature scheme extension has a specific number as an extension. So in the extensions field, you'll find it. It gotta have a number. Let me just. There we go. An extension looks like that. So an extension type followed by the extension data. You find this a lot. In a lot of cryptographic encoding, there's going to be a thing that tells you what the rest is, and then the rest. And even more often, there's a thing that tells you what the rest is, the length of the rest, and then the rest. Tag length value, TLV. Very, very common. Why is it useful? If you don't know that extension, you can skip it. Like you see an extension that is not in this list. It's extension number 115. You have no idea what it is. Okay. You go to the next byte. Next byte tells you the next 2 bytes. Sorry, because it's up to do the 16. And you need 2 bytes to represent 0 to the 16 minus 1. You take those 2 bytes, and that's the length of the extension. And then you just skip that many bytes, and then you find the next extension. So you can ignore an extension you don't know. If instead you know it, because the extension is number 13, then you know from the specification that it looks like this. Itself a list of numbers from this list. And these are the numbers of the signature algorithms that are supported. So by decoding pieces out of that client hello message, the server now knows which signatures are supported, which key exchange are supported, which ciphers are supported by the client. And that's that part. Make sense? Cool. The server picks. This is not all protocols. Some protocols do something, honestly, sillier, which is that the client sends a list and the server sends a list, and then there's a specific algorithm to choose which one wins from the overlap of the 2 supported lists. I like the TLS model a lot better, where the client sends a list and the server has authority to pick the one that makes most sense. So the server will receive a list of signature algorithms, a list of key exchange mechanisms, a list of ciphers, and will choose one for each of these and put it in the server hello. This is called negotiation. Does it make sense? How there's a preference list and there's a choice from the other side. Negotiation happens a lot in in basically all of the synchronous protocols. Great. Then what happens? Let's see, what do we talk about next? Next, we talk about the key schedule. So now we've chosen the parameters, and everything up to here is unencrypted. It has to be, because the client has nothing to encrypt it with when it sends it, and the server needs to respond which things it chose before the client can agree on the key. But now that we've agreed on what the options are, we might be ready to derive keys. Why might? What do you remember about MLChem? How does MLChem work? One side generates a public key, sends it to the other side. The other side encrypts a key, generates a ciphertext, sends the ciphertext back. So what does the client need to send for the server to be able to generate the key and encapsulate? The public key, just the public key. The client just generates the public key, a fresh public key, and sends it over. The server picks the random encapsulated key, encapsulates it into a ciphertext, and sends the ciphertext. That's what the key share is. Can you see a problem? We just said that we negotiate the supported key algorithm, the key exchange algorithms by the client sending a list and the server picking. How does the client know to use MLChem before the server has responded?
You just send the data for each possibilities.
Except, what do you remember about MLChem? That MLChem public keys are large. So we can't send too many of them.
I think something we can do is like the server can publicly announce that we want this to be done this way.
That exists. Well, will exist soon. It's called hinting, but publicly needs a place where the client can find it. And unless you can somehow bundle it with all the information the client already needed from the server, that adds a round trip, because the client needs to go to this public place to get this information before it can start the connection. But it will exist, and it's if you're curious, it's based on DNS. DNS is the system that turns names into IP addresses, so you need the IP address of the server anyway to connect. So the idea is that the client, at the same time as that it asks, hey, can I have the IP address of google.com, will also ask, by the way, do you know which, has google.com published which key exchange algorithms it prefers? And then it gets back that list together with the IP address at the same time, because it's a single round trip if you ask for two things without waiting in the middle, and you get those two answers in a single flight. And then it has that. That will exist. Does not exist yet. The answer is that it just guesses. And then there's a mechanism called hello retry request, where the server can answer, you guessed wrong, use this one. And then you just repeat from the top, but using that one. Which is simpler. Like, it's simple and it works. So, hey.
Like, I don't necessarily, what if your guess is wrong?
If you guess wrong, instead of getting a server hello message, you get a hello retry request message, which is a different message. It has a different byte at the beginning, so you can tell them apart, because again, everything is type, length, value, approximately. And you get back a hello retry request, which is a message that says, I don't support that one, use this one.
But that's like another round trip.
Yeah, you lose a round trip. If you guess wrong, you lose a round trip. So there is this tension. Either you make your client hello very large to avoid the risk of extra round trip by sending multiple things in the client hello, or you risk the round trip. You could even choose to not predict anything. Send an empty key share at the beginning. The key share is the public key. That's what key share over there is. Because it's the client's share into the key derivation. It's side of the. You could even decide to send it empty and always get a hello retry request. And then TLS becomes a 2 round trip handshake instead of a 1 round trip handshake. Browsers don't do that. Browsers these days send MLChem 768 mixed with elliptic curve Diffie-Hellman over the X25519 curve, and just the X25519 curve as two separate algorithms, because this one is fine and it's backwards compatible, and servers have mixed support for the new post-quantum stuff. So this way it's a single round trip with both older and newer servers.
But if I understand correctly, it's just like time versus memory tree. Like, one side you can just retry with small chunks, like spend a big chunk and just
time versus bandwidth. Round trip versus bandwidth. Yep, it's a hard round trips versus bandwidth trade-off. Correct. And this is the bread and butter of protocol design. Yeah, so much stuff is thinking about these dynamics and thinking about the clients will be, will the servers update, and like what pressures are we putting on the ecosystem, like can the ecosystem upgrade easily, this was fine for going from classic elliptic curve to MLChem, because classic is cheap. So we can keep sending the classic one and send the post-quantum one. This mechanism will not be good if we ever want to change which post-quantum algorithm we are using, assuming that the new one is not very cheap, which we're kind of using compound. Because now we will have to send two expensive ones, two large ones. And so the work is being done on the TNS-based pre-hinting to work around that. Yep. It's about time for a break, so we can talk about how those keys are used afterwards, but essentially we've talked about everything up to here. The key share on that side, can you imagine what it is?
It's the private key.
Not the private key. The private key definitely does not go on the wire.
No, like you send the private key to the public key and you send it to the...
It's a ciphertext, the encapsulated shared secret. Yeah, it's the encapsulated shared secret. So the key share in the client hello is the public key. Public key flies over, the server generates a new shared secret, encapsulates the shared secret using the public key, and sends the encrypted, encapsulated shared secret back as the key share. So when the client reads up to here, it's ready to decapsulate the shared secret using the private key that it kept from having generated it. Notice how I'm using public and private key for the things the client generates, and shared secret as the thing that the server generates and sends over to the client. So the ciphertext gets decapsulated by the client, and now the two sides have a shared secret. So from this point, they can start encrypting. And indeed, notice how these squigglies appear. Those are encryption. We can talk about how to test as encryption in a minute. Do you have questions about up to here, like the key exchange part?
Yeah, I don't know, like, so the client gives the public key, and the server takes the public key of the client, and then yeah, you give back the encapsulated key. Which is like the mix of the public and the private, the public key of the client and the private key of the server.
The server here doesn't have a private key. The server generates a shared secret, which is specific for that connection. Remember the two operations that MLChem does for us. There are, well, three. Key generation, which produces a public and a private key, done by the client. Encapsulation. Encapsulation is what the server does. Encapsulation is a function that takes a public key and produces a ciphertext and a shared secret. The shared secret stays with the server, but is the thing that the client will also figure out once it receives the ciphertext. The ciphertext is the thing that is safe to send over the wire, because without the private key of the client, cannot be turned into the shared secret. So keygen, encapsulate, which produces a shared secret that stays over here, and a ciphertext, which goes in here. Decapsulate. The client receives this and runs decapsulate, which is a function that takes a ciphertext generated for the public key and a private key, which was generated together with that public key, and produces the same shared secret that was generated by encapsulation on the other side. So keygen, encapsulate, decapsulate, result. Over the wire, we've had just public key and ciphertext, two things that, even if the attacker knows them, can't do anything with. And on the two sides, we have a shared secret. From there, we can do symmetric encryption. Ignore authentication for now. We're going to do authentication here. let's take a break. Back to TLS. We've established shared keys. Now we need to derive keys, and that is the key schedule, which is a fancy name for, guess what? Hashes. Obviously hashes. So this is the structure of the key schedule. You can ignore the PSK for a second and actually ignore all of the early stuff. There is stuff in TLS 1.3 to start sending data after 0 round trips, like with the client immediately starts, by using the fact that you already connected to that server in the past. So you use some key that you kept around, you saved from the last time you connected to the server to start encrypting immediately. That's ignored. Let's say that this is a fresh connection. So you start here. ECDHE is actually ML10 today. This is the key exchange. The spec is from a different time. It's from more than 10 years ago. Yep. HKDF. Do you remember HKDF? It's using hashes to do key derivation. It's the thing that does HMAP. HKDF gets, we use HKDF with the stuff from before, which can be 0 for our purposes, and MLChem to get the handshake secret. Once we have the handshake secret, we do derive secret to get the handshake traffic secrets. Derive secret is more HKDF. And the arrows are the inputs to HKDF. And the outputs are the various method keys. So we take the MLChem shared secret, that comes from the left over there, to derive the handshake secret. And then we use the handshake secret to derive separate keys for the client and the server. We use the client one to encrypt the things that go from the client to the server, and we use the server one to encrypt the things that go from the server to the client. And then we do another round of derive to when we switch from the handshake to the rest of the connection. This part doesn't, you don't have to worry too much about it. It's just to separate encryption of different parts of the handshake. So the things with the squiggly, with the curly braces are encrypted with handshake secret, and instead the ones with the square are encrypted with the next secret. Why? Because the other thing that we include when we do key derivation, which here is hidden in this stuff, is the transcript. Transcripts are an important concept of protocol design. You don't want the two sides of the connection to think that different things have happened. For example, you don't want to successfully establish a connection where I say, hey, I can do TLS 1.2, TLS 1.3, I support MLChem and LDSA, and also support elliptic curve Diffie-Hellman as a fallback. You don't want me to say this and the other side to think I said I only supported elliptic curve Diffie-Hellman, because that's a downgrade. If you're an attacker in the middle and you have a quantum computer, so you know how to break elliptic curve Diffie-Hellman, but not MLChem, you want the two parties to negotiate ECDH, right? Because that's the one you can break. So you want to avoid the situation in which I think I said I support MLChem and you think I said I don't. Because if you think I said I don't support it, then maybe you will accept to use elliptic curve Diffie-Hellman because you're like, well, if the client does not support anything better, this is better than nothing. So this opens the door to a downgrade attack. The best way to avoid downgrade attacks is to not support the weaker stuff at all. But that's not practical, oftentimes. Why is it practical? Because sometimes you have to keep working with the older stuff as you roll out support and updates for the newer stuff. So what you do is you mix it into the key. The actual client hello and server hello go into the key. So since the client hello has the list of things I support, and the server hello has the list of things the server selected, if an attacker in the middle removes some stuff that I said I support and you, so that you think I don't support, we will derive different keys. And so what will happen is that when we do the handshake, you're going to derive these keys based on the client does not support MLChem. But when I try to decrypt it, I will try to decrypt it using a key that instead was derived from the client does support it. And early versions of the protocol included things into the key, just piecemeal. Went like, oh yeah, it's important to agree on that part. So let's take that part and put it into the key chain. Over time, we realized that no, the best thing to do is to take the transcript of the entire connection, just hash it into the key. So we agree on everything that was sent from both sides. Transcript. So up to here, we derive one key with the transcript up to here, so that we can encrypt the rest. Then we do this stuff encrypted, and then we this finished is the hash of everything happened until now. It's just a message to make sure that we agree on the transcript, indeed. And then we derive a new key, which has the transcript up to here. That's why we change keys, so that we can we can start encrypting from here, but then we can later fold this part into the final key. Make sense? Cool. What is this part? This part is the authentication. So a certificate is the thing that contains the public key and has the signature from the third party, which is known to the client. This is how the client learns the public key of the server. It doesn't just trust it, because otherwise the server could just lie, right? Instead, the certificate is signed by someone else, but that is outside of the scope of TLS. So TLS just has a space to send the certificate, but the certificate is just a bunch of bytes. What you do with it is a different protocol, X509. Right, so the certificate is sent and then certificate verify. Can you imagine what certificate verify is? The certificate is just, here is my public key, and proof that this is actually the public key of chasebank.com, because the certificate is signed by a third-party CA that you know, which attests that this is my public key. Great, now you have my public key. What do you do in the certificate verify message? What step are we missing?
At the certificate point, am I already? I mean, the client is it already certain that the server is who is saying is, or do we still need that certain? So maybe we just I just say, I don't know, I encrypt the word hello with my key, then I send you, and this is certificate verified, and the client unpacks it, and it can unpack it only if it's done by the server. So
Almost, but remember we're using signatures here. So up to here, we've learned the public key of the server, but we have no proof that the server actually has the private key. These are not the public and private keys of MLChem. Those are generated fresh just for the connection, and they are completely separate things. This is the long-term public key of the identity of the server, the one that that is certified to be the actual public key of chasebank.com, and how we know it's chasebank. Up to here, there's nothing telling us that the server is not just lying about having the private key.
encrypt maybe the transcript or something else using the private key, and then the client can check it.
Yes, except we don't encrypt. What do we do with signatures? We sign. Yeah. So it's a signature over the transcript. Exactly. So it takes the transcript or the transcript. Yes. It's a signature over the transcript hash. That's it. The certificate verified is that signature. The client receives it, checks the certificate, makes sure that it trusts the certificate. That part is out of scope. Takes the public key out of the certificate, uses the public key to verify the signature over the transcript from the server. Now, it's sure that it's actually talking to traceback.
What is the difference between like encrypting and signing? Is it just that I send also the plain text when I sign?
There is nothing secret. Two things. The message is public, so not secret. And second, the private key, public key rules are reversed. The signature is made with the private key and is verified with the public key. While if I encrypt something to you, I would have to do it the other way around. I would have to send you something encrypted because only you with the private key can decrypt it. And this is how TLS 1.0 worked. TLS 1.0 used RSA instead of using signatures. But this had two problems. You can't do that with one round trip. At this point, the client doesn't know the public key of the server, so it can't encrypt anything to it. So it has to first wait for the certificate. When the certificate comes, then it has to encrypt something and say, hey, can you decrypt this? Yeah, so it requires that extra round trip to do the encryption-based one. The other thing is that signatures are publicly verifiable. You can show a signature to anybody and a public key, and they will see that it's actually a signature from that public key. Instead, if you encrypt something to someone, only they can decrypt it, but you can't prove it to someone else that it happened. This is called third-party verifiability, which doesn't matter for TLS, but it is a property of signatures that for other protocols can be important. Yeah. Again, you could build TLS with CANs by using CANs to authenticate things. You could. It's just that that's not what we have. And it has the 0.5 round trip problem. Okay, so at this point, the server can start sending data, which would not be true if you had to do the outcan, the thing where you send a challenge to decrypt, etc. It can start because at this point the key has been derived, so it can start sending. The client will first verify the stuff and then start decrypting. If the verification fails, it trashes everything that it received. And then the client, for its side, it can also do a certificate verify if it wants, if the server asks, and then it derives its own key and start sending data. This is not used often, the 0.5 round trip data. Usually the client is the first one to speak. Usually. Because usually what you're using this for is to make a web request, and the client has a request for the server. So the server gets to hear and then stays silent and waits for the client to send this and its first application data. Usually. Which is why you could do the CAN-based thing. The only problem with it is that the client would have to start sending data before it knows whether the server can decrypt the thing it sent correctly, which is fine because if the server can't decrypt it, it can't decrypt the application data either. But it's a little abstraction breaking. Like the client is starting to send stuff and it doesn't yet know if the server is actually authenticated or is And if the server is lying, true, it will not be able to decrypt this stuff, so it doesn't learn it. But maybe you were assuming that if the connection succeeded and started, it meant that the server was honest, and then you might get confused later. Like, it's the sort of thing that it's the vulnerabilities that live in the layer between two parts, between the TLS and the application. And those are really hard to reason about, because what does the application do? Who knows? There are millions of applications. They do stuff. So maybe they make assumptions, maybe not. It's really hard to think about how things interact. It's a lot easier to prove, yes, if these are the theoretical properties of TLS, it satisfies them all. A lot harder to figure out what the implicit expectations could be. And that's true of all of security, by the way. Much more often, the software security issues are in where components get in contact with each other. Okay. Does this make sense for TLS? Does it give you an idea of how a real-world protocol looks like? Questions about TLS before we move on to other protocols?
Are alternatives, or is this basically ubiquitous?
Basically ubiquitous. For transport security, it'd be really weird to not use TLS. It's kind of a red flag. Companies that reinvent TLS, it's always like, what are you doing? Why are you doing that? There is one thing called a noise, which is a much more flexible protocol and more lightweight in some ways. And you can use it also for connections. And as far as I know, WhatsApp uses it for the connection to the server. Although there is no standard way to do post-quantum noise. There are a few designs, but so I don't actually know what WhatsApp does about that. See, part of the reason you don't design your own is that then when stuff like post-quantum happens with TLS, you can just be like, yeah, all right, have you figured out post-quantum TLS? Great, I'm going to adopt that. If you have your own, you have to redo all the thinking and do your own changes for post-quantum, for example. There are a lot of other protocols for other things. A very popular protocol is SSH. SSH is the protocol used, it's the secure shell protocol. It's the protocol used to connect to a server to send commands or transfer files. It's generally the secure way to connect to remote shells, remote machines. And it's older than TLS 1.3, and that kind of shows its age. But at the same time, it's fairly well designed, and it survived a lot better, which is part of why it's still, like, we had to redo TLS 1.0. We did not have to redo SSH 2, which is the current version. There are people that designed like versions of SSH on top of TLS and stuff like that, and even had the arrogance to call it SSH v3, and nobody liked that. There needs to be enough good reason to move to something new. Not being a little better does not cut it. And it was not from the SSH working group or from the OpenSSH implementers, so that was a little weird to just coming in and say, oh, we've made SSH 3. Yeah. And a lot of this stuff is social. Like, so much of the world of designing is about human systems interoperating and working together. So SSH works similarly enough that I don't think it's worth looking at. it similar, different idiosyncrasies, but the idea is the same. Protocols that are different. MLS is the open version, TLS style, PLT, the IETF of what started as the signal ratchet protocol. The signal ratchet protocol is the signal app, the messaging one, and it's a protocol for two or more people exchanging messages which are asynchronous. Like TLS, everything is in order. We never discussed what happens if this arrives before that. It's an error. Like, if you don't send things in the right order, you're out. Messages are different. Messages can get delivered out of order, they can get lost, they can you can have a different view of the messages of sent by two people than someone else, because you may receive the ones from that person before that other person, and someone else receives them in the other order between the two senders. Generally, chat session can span years, while a TLS connection spans hours, minutes. So there's a lot of things that are pretty different. One concept that's useful to know when talking about protocols is the concept of forward secrecy. We briefly touched upon it a couple of weeks ago. It's the idea that there is no secret here that will still be held in a year, and it allows decrypting this connection. Like here, there's the ephemeral secrets, the shared secret, the secret keys of the connections, the private key of the key share. All of those, as soon as the connection is over, they're deleted. And then there's the long-term key of the certificate, but that one is a signature. It doesn't let you decrypt anything. It only lets you fake a signature if you have the private key of the signature algorithm. So if in a year somebody compromises the server or the client, they can't retroactively decrypt this connection, because in a year all of the ephemeral keys will have been deleted. And the only key that might still be alive is the certificate one, but that one doesn't let you decrypt it. It only lets you fake a signature in the future, not in the past, because time moves forward. So this property is called forward secrecy, and if you don't design for it, you usually don't get it from a protocol. You have to be a little careful about making sure that all of the secrets are ephemeral and can be deleted at the end of a connection. It's a little harder for messaging, because you need the messaging session will last years, right? So what MLS and the Signal do is called a ratchet. So they do multiple exchanges, like the key share, periodically. And in doing that, they then include derive new keys using hashes from both the old keys and this new exchange, and move to those new keys and forget. So if you compromise a key later, you can only decrypt maybe the last 10 messages and not the last year of messages. So there's one way a different setting changes how you need to design the protocol. The other difference is that generally there isn't a certificate for people. Like, you don't have your certificate, right? So instead, generally authentication is done either with systems of key transparency, which we can talk about maybe tomorrow, or with the security numbers. I don't know if you've ever seen the screen, but there's, if you go in Signal, you open the chat with someone, and then you tap view safety numbers. It will show you a QR code. That QR code is the hash of both your long-term public key and their long-term public key, just concatenated. So if you scan each other QR, you know that you have the right public keys and there's no nothing in the middle. These are the equivalent of the public keys that go into the certificates. This is generally a hard problem because people don't do that. And so it's debatable whether it helps or not. The argument in favor is it helps even if just a few people do it, because then the attacker always has a risk of getting detected. Even if not all the cases get detected, if two people scan their QRs and the key is not right, they know that Signal is faking the keys, and that would be a whole thing. The argument against that is sure, but they will probably target specific, I don't know, activists that have a lot of better stuff to do than compare QR codes. And they will do it when they know that they will not meet in person, and so they will never get detected. So there are better systems like e-transparency. We can talk about it tomorrow. Yeah, those are the major differences. Then, what other protocols was I planning to? Oh, and then there are things that stretch a bit the definition of protocols, but I think fit still in the concept of protocols, like file encryption. How do you encrypt a file? Kind of an easy thing, but also still you need a protocol. You need to agree how you do the wrapping, and you need to agree also what is it for. Do you want a file to be decryptable by multiple recipients? Do you want it to be authenticated? Do you want it to be signed? And AGE is a small file encryption format and library and tool that does that. And the format is a protocol, except it's a non-interactive protocol, because you learn somebody's public key, or you have your public key for your backups or something like that, and then you encrypt a file to that without actually talking online to the recipient. You just encrypt the file and then you attach it to an email and you send it. So there is no interactivity. And this is how it looks like. There's just a bit of header so that you know that the file is encrypted with that. Then this is the equivalent of those IANA numbers. Instead of using the numbers, we use the actual name. So this one is encrypted using X25519, but there are post-quantum ones now. This one uses MLCAM. And that says, okay, I've encrypted this file to an MLCAM public key. Can you guess what this is? A very, very long string. I'm using MLCAM. So probably if I'm encrypting to somebody's public key, what will I have to send? The public key I have it, because the public key is encoded, is the thing I'm encrypting it to, and this is the public key. So I say, okay, I will, essentially it goes like this. Hey, if you want to send me an encrypted file, here is the public key you can encrypt it with. And I publish this on my website, for example. This is the public key. It's very, very long. When I tell you that MLCAM is large. This made AGE a lot less usable. This is what the public keys used to look like before. This is how the public keys used to look like before post-quantum. And these were the private key, the secret keys. And now the secret keys are still small. Why? Because secret keys never have to be large. Because you can always take 256 bits of entropy or 128 bits of entropy and expand it with whatever algorithm into whatever key it had to be. Because 256 is all you need to become unpredictable, and then the rest is just a deterministic algorithm. So secret keys are never large. But yeah, the public key is this now. Which, not the end of the world. You can copy paste it, but It was nicer when they were shorter, but yeah, we don't get to have nice things anymore. So the public key, I put it on my website. And if you want to encrypt a file to me, you put the public key into the program and it encrypts the file. This is the thing that actually goes into the file when you encrypt it. What is that going to be? Yes, exactly. That's the encapsulation of a shared secret. Then that shared secret is used to encrypt the actual file key. Why are we doing this two-step thing? Why don't we just use the shared key to encrypt the file? Because this way we can encrypt the same file key with many different shared secrets so we can encrypt the same file to many different recipients. If a file is 10 gigabytes, it's nice to encrypt it with one symmetric key once, and then encrypt that that secret key with the shared secret of each recipient, which requires just this little part. So we can have multiple ones, 1, 2, 3, 4, so that the file can be decrypted with 1, 2, 3, 4 different private keys. And AGE is pretty much just this. A bunch of these that encrypt the file key, then HMAC, which is the transcript, HMAC over the header, which is the transcript, and then the encrypted file, which works pretty much the same as TLS in how it chunks things up. It's not literally like TLS because I had not realized it should be like TLS, and version 2 will be literally the TLS way of chunking things up. Because why analyze things twice if they are serving the same purpose? You can just reuse the same design so that you can use the same papers that already looked at all of the combinatorics and all of the collisions, risks, and the bounds and stuff. Right, so this is an example of a non-interactive protocol. Make sense?
Do you have like a diagram like for
Say again?
do we have like a small diagram? It's easier to
Yeah, I'm afraid I don't. But also you would see just one arrow
it's just
and nothing else.
yeah, that's
Because there's essentially just the client hello and then immediately the application data. The client hello is this, which is a header which says I'm using this key exchange. Here is my key share. Then this is just a encryption of the file key, and then the rest is encrypted with the file key. So there's just one arrow because again there's no interactivity. So the thing goes over, and you don't get to have a response and react to that and do exchanges. Quiz. What does this mean for forward secrecy? Yep, there's no forward secrecy. If you compromise the secret key, you can decrypt all of the files that were encrypted to that secret key. There is no forgetting of keys happening here. If you compromise the recipient key, the sender destroys everything as soon as it's done. It destroys the shared secret. It destroys the file key. It only uses it once, and it's fine. If you compromise the sender might have deleted everything. If you compromise the recipient private key, then you decrypt all the files. Why is that okay? Because that's the purpose of the protocol. The point of a file encryption tool is that you still decrypt your files in a year. Like, do you want to be able to decrypt your photos in a year? Yes. Do you want to be able to decrypt your TLS connection to your bank a year later? No. No, that connection happened, it was over, it needs to be buried. So different purposes, different properties, different shape. which is why it's important not to use a thing for the wrong thing. People ask me, can I use Agate to encrypt my emails? No, no, absolutely not. Why? Because then somebody compromises a year your secret key and decrypts all of your emails from the past year. Bad. You use Signal instead. Or you just use an encrypted email and you accept that if somebody pops your mailbox, they have all your emails. Okay. But if you wanted something secure, you use Signal. And if in a year your phone gets compromised, they don't get your old chats unless you stored the chats on the phone, of course, like if you've saved them. But if you delete the chats and they recorded the connection, they can't use that to decrypt it. Well, here, if they recorded the emails as they were being sent and then they steal your Agate key and you're using Agate to encrypt your emails, you're done. So a lot of using cryptography well and deploying cryptography well is knowing when to use what. And you have no idea how often I get asked, can I use Agate to encrypt my emails? There's history to why I ask this question, because Agate was made to replace the last remaining use case for GPG, which is a tool that implements a protocol, which is OpenPGP, which is a protocol that instead tried to do everything. It was how you encrypted files, how you signed public messages, how you encrypted email, and people still do email encrypted with PGP, and it has no forward secrecy because it's not a protocol specialized to a job. But the specialized thing for the job of messaging is MLS, is Signal. Agate just filled the gap of, okay, but what if I just want to encrypt a file in a way that I will be able to decrypt it forever? Agate exists, but then people are like, so Agate is a replacement for GPG, so I'm going to use it to encrypt my emails. Like, no, that was the entire point of making Agate, was to stop you from using a single tool for everything, because you can't do well 10 different things. You just can't design a good protocol that does many things at once, because we just saw how different things have different requirements. Questions? Or you're free.